Kinematics is known as the study of motion without regard to forces. So some key concepts here involve displacement, which is just the change of position, and velocity, which is the speed with direction. And then acceleration, which is the rate of change of this velocity. So what is a PT graph? A position time graph. On the x-axis we have our time, and then here we have distance in the y-axis. So let's say we have this PT graph over here. We can interpret this in 3 distinct sections. So in section 1, our time, we go from 0 to 2 seconds, and our distance, we go from 0 meters to 4 meters. Speed can be denoted as v without the arrow on top. With the arrow, that means that it's a vector, meaning that it's with a direction. But when it's just with a value and no direction, that's the scalar. So right here we have our scalar, which is just speed. And this will just be the difference in distance, so delta d over delta t, which is the difference in time, which will be equal to d2 minus d1 over t2 minus t1. Okay, so if we want to calculate our velocity in section 1, then we can just say v1 or v section 1. So in distance 2, we have 4 meters, and distance 1, it's 0. So it'll be 4 minus 0. And for the time, we're going from 0 seconds to 2 seconds, so it'll be 2 minus 0. So v1 will be equal to 4 over 2, which means that our velocity will be equal to 2 meters per second. In section 2, which is this area, notice how there's no change in distance. We're staying at 4 meters, and we can interpret v2 as 4 minus 4 over 6 minus 2, and this will just be 0 over 4, which means that this will just be equal to 0, which means that around this area we are stationary. Okay, now in V3, we're going from 4 meters to 8 meters and from 6 seconds to 8 seconds. So V3, 4 over 2, which will be 2 meters per second. Now, let's look at another example, this time of something known as a velocity time graph. This will just be time on this axis and velocity on this one. So if we have a graph that looks something like this, then we can assume that around here we are accelerating and acceleration, by the way, is just delta v over delta t. Delta v being the change in velocity and delta t being the change in time. Then what we can say about this acceleration is that it will be 2 meters per second minus 0 meters per second, and from 0 seconds to 4 seconds. That means our overall acceleration was 2 over 4, or just meters per second squared. Next up, let's talk about calculating velocity and acceleration. So if an object moves 20 meters in 5 seconds, then velocity will be equal to 20 over 5, which would be equal to 4 meters per second. If velocity changes from 0 to 10 meters per second, then in 5 seconds, then our acceleration will be 2 meters per second squared. And I won't go into too much detail about the kinematic equations, but here are some of them. And so you might be wondering, what are these equations? These are the essential kinematic equations, which pretty much, if you have certain variables that you have and some unknowns, then you can use any one of these equations to find the missing variable. Okay, so now let's get into forces, what is a force? A force is a push or pull that can change an object's motion. So these are measured in something known as newtons, and their value is just N, or unit of measurement is just N. And there are different types of forces. There's gravitational force, which can be written as Fg, mass times the speed of gravity, which is negative 9.8 meters per second squared. And the general formula for force is just m times a, where m is the mass, a is the acceleration. And then we have normal force, which is the force from a surface supporting an object, which is always perpendicular. We have friction force, which opposes motion, depends on surface and normal force. We have applied force, which is any force applied by a person or object. We have tension force, which is a pulling force transmitted by a string or rope. Let's talk a bit about drawing forces diagrams. So let's say we have a box that is on a normal surface. Then we have a couple of forces acting upon it. So we have a downward force, which is Fg. We have the normal force, which is Fn. We have the applied force, which, let's say, horizontally F applied. And then we have the friction force, which is F. So let's say we have a problem where we have a 10 kilogram box that is pulled with a 40 Newton horizontal force. So Fg on this box, let's just first draw a diagram of this. That's not very straight. Let's draw a straighter line. So you have a box and it's being pulled horizontally with 40 newtons of force. So first things first, this will be F applied. Downwards will be Fg. Upwards will be Fn, the friction force. So first of all, let's calculate Fg. Fg will be equal to 10 kilograms times on Earth, which is 9.8 meters per second squared. So Fg will be 98 newtons of force downwards. And then the normal force will just cancel this out since it's just laying there. So Fn will just be 98 newtons as well, but this time upwards. So now we have a friction force. So let's say there's a friction force of 10 newtons that is opposite to the applied force. So let's calculate the net force. So F net will be equal to the force applied minus the friction. So here it will be F net is equal to 40 minus 10 newtons, which will be 30 newtons total. So that will be the F net. And so if we want to find the acceleration of this object, then it would be A is equal to F net over m. So it would just be 30 over 10, which means that our object is traveling at 3 meters per second squared to the right. So now let's talk about Newton's laws of motion. So Newton's first law, the law of inertia, states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and direction unless acted upon by a net external force. The second law is the law of acceleration. So the acceleration of an object depends on the net force applied and inversely on its mass, which is the formula we just learned, which is F is equal to ma, mass times acceleration. So if you apply a 10 Newton force to a 2 kilogram box, then to calculate acceleration, then A will just be equal to the force divided by the mass. So A, in this circumstance, would be 5 meters per second squared. So finally, we have Newton's third law, which is for every action, there is an equal and opposite reaction. So an example would be a rocket expelling gas backwards to move itself forward. So the gas moves backward here and it moves itself forward. Now let's talk about energy. So there's different types of mechanical energy. Energy exists mainly in two forms. We have potential and we have kinetic energy. So potential is basically just stored energy based on an object's position or configuration. And we have kinetic energy, which is the energy of motion. So let's talk about some formulas. So gravitational potential energy will just be mgh. And kinetic energy will just be 1/2 of mv squared. So first things first, let's say we have a ball at height h, which is equal to 10 meters above the ground. Then we have the mass of the ball, which is m equals, let's say, 2 kilograms. And now let's say we have the arrow downwards, which is the Fg applied on it, which means that if the ball was just sitting here, 10 meters above the ground, then the potential energy of this ball would be Pe is equal to mgh, which will be equal to 2 kilograms multiplied by 9.8 meters per second squared times the height, I'm running out of room, of 10 meters. So overall, our potential energy will be 196 joules, which, by the way, energy is measured in joules. Now, let's say instead of the ball just sitting 10 meters above the ground, it instead falls. So it's now in free fall and it's not being supported by anything. The only force acting upon it now is Fg. There's no counteracting Fn force. Now, what this means is that essentially our potential energy, our Pe, will now be converted into kinetic energy. Now, let's talk about the concept of conservation of mechanical energy. So the total mechanical energy of something will simply be the potential energy plus the kinetic energy. So this will remain constant in a closed system without friction. So example, the ball converts all the potential energy to kinetic energy when it reaches the ground just before impact. Finally, as the last and final concept we discuss in this video, we're going to be talking about momentum, which is denoted as P, and it's simply just mass times velocity. And momentum represents the quantity of motion. So momentum is conserved in isolated systems. So let's say we have an example where we have cart 1 of mass 3 kilograms and its velocity is 4 meters per second. And then we have cart number 2, which is 2 kilograms, but its velocity is 0 meters per second. So let's calculate the momentum before collision. So this is before these two collide. This will just be P is equal to 3 times 4 plus 2 times 0. Okay? This being this cart's momentum, this one being this cart's momentum. If you were to calculate this, this will just add up to 12 kilograms meters per second. And then after collision, our velocities will change, but the total momentum will be 12 kilograms meters per second. So momentum in this case is preserved. It's conserved in isolated systems, which means that if this is an isolated system, then pre-collision our momentum will be this, and post-collision it will remain this as well. Congratulations, because you've just learned the basics of Physics 1.